Welcome to your weekly installment of Geography 316, Methods of Analyzing Geographical Data. So this is going to be kind of a walkthrough explanation of Lab 3. We're going to talk about data structure again, which hopefully is somewhat of a review for most of you, having already done the online tutorial. And then we are also going to talk about descriptive statistics and start plotting with histograms. So this is the first time we're really going to get into the kind of why we're using R, what is it good for? Well, we're going to use it to do statistics. So you will go to Blackboard and there will be a link to this HTML file, which is the lab document. So again, you can see as you scroll through, the table of contents expands. You can also click on sections to go back to where you left off. Also, I think there's only one in here, but if you ever see text, bold text in red like this, if you hover over it, it'll pop up the definition. All right? Don't tell me I know. It is pretty cool that I can do this kind of stuff. All right, so you're going to, on your computer, go to your R project where you have been saving your labs. Open that. And just as the same as we did for the last lab, you're going to create a new R script, save it as your last name, and then this is lab 3. All right, and so you can see there it is. So coming back to our HTML document, let's start off with the data structure. So here we're going to talk about the more complex structures. And so common among those are lists and data frames. So first we'll talk about lists. So if you remember that a vector is a sequence of elements that are all the same data type. So you might have a numeric vector or a character vector. Lists are similar except that each element can be a different data type. So you can have a list where one element is a character and the next is numeric. And then, infinitely on, they can be as long as you want. The elements in a list can even be other lists or data frames, so you can get these complicated nested structures. So the basic function for creating a list is surprise list. And so what you're going to do with this document and what you're going to turn into me is all of the code that you see in these code blocks I want you to run in your own script because I want you to see what they do and I want you to get used to learning to type them. So here you see this. We're going to make a list with these 3 elements. So I want you to do that here. The nice thing about RStudio is as you start typing, it comes up with this list of suggestions for you. And because a lot of what we're doing is pretty basic, usually what we want is going to be right on top. So you can just navigate with the arrow keys and then hit enter when you find what you want. And it pops it up there for you. It auto completes. And the nice thing too is it's always going to put you inside these parentheses, which makes it a lot harder to forget to close them. Because if you forget to close the parentheses, then your code is going to fail. You're going to get a warning. So here we're going to make a list. And we're going to run it. So you can hit run here. You can also, there's this shortcut. See, it says it right there. On a Mac, it's Command Enter. I imagine on a PC it's Control Enter, but I'm not sure to run that code. So you can see it down here. We've created our list. It has 3 elements, which is this 1, 2, 3 in the double brackets. And each one of those elements has 1 element, 4, 2, 3. Right? So this kind of explains that there. To talk a little bit more about these indices that you see printed because they were honestly confusing to me for a long time. These double bracket parentheses here refer to items in a list. These single ones are just the regular element indices. And so if you make a sequence, so this is just a numeric vector, 1 to 100, and you print it here, you can see that each one of these numbers has an index, but R only prints the index of the first element in each row. And so actually, if you made your console window smaller and then ran this code again, you can see that it's printed different indices. It's just kind of a way for you to kind of keep track visually of what you're seeing in the console. So you can also make a list with items that contain more than one element. And so here, make this so I can actually see it. There we go. We're going to make a 3-element list. Where each of those elements has 3 elements. So now you can see here, we still have our 3 elements, each of which has 3 elements. And this just takes you through some more examples of how to make that. Remember that the C stands for combine or concatenate, which is the more programmy term. And it just means to combine things, right? So this is a vector with 3 elements. This is going to be a vector as well, but it's going to have 5 elements, 3, 4, 5, 6, 7. So I want you to run all of this code, type it in, run it, and then you're going to have some questions in these blue boxes. So then once you've run all of this code, you're going to come in with a comment. You are going to answer the question in the blue box. And so these are peppered throughout the script. So another thing that lists can do is have names for the items in the list. All right, so I'm going to walk you through the rest of this using an R document that's going to look different than the script you are writing, because I have already typed all of this in to create this wonderful lab manual for you. I feel like I shouldn't have to do it again. So I'm just going to run my code explaining things from this R document, but you need to write it yourself in your R script. All right, so let's see, where were we? All right, names. So we've created this list for, you can see it here. These are the items in the list. These are the classes of those elements. So let's examine the names. And they are null. That's because we haven't given any of those items names yet. They don't have to have names, you don't need them, but sometimes they can be helpful. So to assign names to items in a list, you just use that same names function here. So names, and then in the parentheses, the variable name of your list, and then for each item, what you want the name to be. These are characters, so they need to be in quotes. So let's run that. You can see here that before, let's go back. It shows the type, the element type. Now it shows the name. right? I've named them. So you could have also assigned those names when you were creating the list in the first place. So in this, we have the name of the item. Notice they're no longer in parentheses. And then the definition of the item. So here I have, so that is in quotes because it's a character. This 3 is not in quotes because it's a number. The logical is not in quotes because it's a logical. So let's print that or assign that. You can see here that they're the same. Now you could have also printed that here, which is what you're going to be doing. List 4, list 5. You can see they're exactly the same even though they were created in different ways. So to select an element, you can either use the index or you can use the name. So you see both of these give you the same result. And using that same method, you can also assign new elements to a list. So here we will create a new list, 1 through 4. Now we can add item number 5. So here we go. You can see here, it's our list. Now, we've added number 5. And we can do it by naming it also. There we go. So now new element number 6. And so you can see here that there's nothing to the left of these colons. Here there is, so that's where the name is. And then you can print the list, and it'll show you that structure. All right, so on to data frames. Data frames are super common in R. It's essentially like a spreadsheet that you would use in Excel. So it has rows, which are equivalent to observations. Say you've got a bunch of patients and you're measuring their blood levels for something that's in your blood, I don't know. And so each of those patients that you measure their blood levels is an observation. And then the measurements and the patient name, things like that, those are going to be your columns, which are the variables. All right, so in order to create a data frame, first you create vectors that are going to be equivalent to your columns. Because in a data frame, each column is a vector, and remember that a vector can only have one data type. Also in a data frame, all of these columns have to have the same length. So here we have run an experiment where we used 2 different kinds of fertilizers on some plants, and then we measured their growth after 3 weeks to see which fertilizer was more effective, right? So each one of these corresponds to an observation, and these are 3 variables. So we'll create these vectors first. Each one has 6 observations. And then we can combine them using this data frame function. So now you can see over here in your environment, this one, our data frame, the fertilizer experiment, looks different than the others, right? It has this little spreadsheet icon right here. So you can just click that and it opens it here. So you can actually view it like a spreadsheet. And so remember that each one of these, there's 1 observation, there's second, or third, etc. Sometimes these data frames are super long though, thousands, millions of observations. So this isn't always the best way to view them, just to get an idea of what their structure is like. You can also use these functions head and tail. I bet you can guess what they do, but I want you to run them and find out, and you tell me what they do. So There are some other useful functions for data frames. So here you would just replace this df with the name of your data frame variable. You can also name the rows. Same as you are able to name the items in a list, you can name the rows. So if we wanted to go through and name our rows for the plants, we could do that. We just use this row names, which right now row names are just the generic numerical index, which is almost always what you're going to encounter and use. Row names can actually get a little bit confusing sometimes, but sometimes they might be helpful. So you can set them using that same row names function here. So now when we open this, it doesn't show there. Does it show here? Yeah, you can see it here. So we've renamed our rows for the different plants. You can set them back to that generic index by assigning them to null. Now you can see they've been set back to numbers 1 through 6. All right. So accessing items in a data frame is pretty easy and cool. You can use this $sign operator to access your columns. So again, see how once you start typing in, RStudio gives you some selections or suggestions, I'm sorry. So this is what we want, this fertilizer experiment. So you just hit enter. And then when you type in that $symbol, it pops up all of your column names. And so you can access it just like that. So there is our growth column, which is pretty nifty. You can also access items in a data frame using an index. Because our data frame has 2 dimensions, there are going to be 2 items that you need to account for in the index. There's the row index and the column. So I run you through some examples here. For example, if you run this is going to be the item in the first row and in the first column. So it's going to give you 1 number back because that's just 1 cell. See, you can see here, that's our treatment 1. And so this would give you the value of the first row in the third column. Right? So this is our growth. This plant had a growth of 1 inch or foot or whatever our experiment was. All right. And so if you want to return all of the columns, you can just leave this second slot blank. You do still need to have the comma to indicate that there are 2 dimensions and you know there are 2 dimensions. So let's run this. You can see it gives you back all 3 of your columns. Let's run it down here. So this is what it would look like on your computer. And so it's the first row from all 3 columns. If you had tried to just do it like this, And same here. This will return all of the rows in the first column. You can also use row names or column names as characters here. You can also call the column like this, which returns it as a vector, and then just use your index here, like we did in the other labs, to index a vector. There you go, 1.1. You can also specify more than 1 row, more than 1 column. So here we have our vector 2 and 3. If you're not using this colon for sequential columns or sequential rows, you need to use the C for the combine so that it reads this as one element instead of several dimensions. All right, so on to descriptive statistics. And I'm just kind of skimming through this because I've put a lot of text in the lesson that will hopefully help you understand this. So for descriptive statistics, we have our measures of central tendency, and we also have our measures of dispersion. So the measures of central tendency are just what that sounds like. How are the measures kind of centrally defined? What is the typical value for a data set? And so the three most common are the mean, median, and the mode. I'm sure you've heard those before. So the mean is just the average of all of the numbers. You add them all up, all of the values, and then you divide by the total number of values in the data set. The median is the middle value, such that half of the values fall below that and half are above it. And then the mode is the most frequently occurring value. And you pretty much only see that one used when the data refers to a count. Because if it's a continuous variable, like you have 1.11, 1.01, 1.32, it's very unlikely, unless you have a very large data set with a very small number of unique values, that the mode would have any significance. Like if you measure the height of everybody in our class to the 100th of an inch, probably nobody is going to have exactly the same measurement. So we would have no mode because each measurement would be unique. All right, and so for this, we are going to use one of ours built-in data sets. It has quite a few. And if you ever start looking on the internet for our help or our tutorials, a lot of people use the same data sets over and over again. And so one of them is this MT cars. So that is this motor trend car road tests from 1975. And so we're going to use that. It's neat. In R, they kind of come, they're already part of your R packages. So all you have to do is load the data, and it'll show up in here, and then you can use it. So the functions for the mean and the median are very straightforward. It's just mean, and then you open your parentheses, you put in the name of your data, and then you hit enter. So here I have you doing it for the cars. We could just as easily do it for, say, this x vector, which is 1 through 5. Let's see what that gives us. So the mean of x is 3, all right, which we could have totally figured out if we wanted to, right? And so same with the median, just like that. So the median is also 3, as you can see very clearly, because this is a normally distributed data set. So to find the mode, it is not quite as simple. There's no built-in function for the mode. But what you can do is create a frequency table. So looking at, let's go to our fertilizer, actually. Let's make a frequency table of our fertilizer experiments using the growth. So you can see here, these are the unique values in that data set. So one of them has 2, which is a growth of 1. So this 1 would be our mode. So the measures of dispersion quantify the degree to which your data set is spread out or close together. So we have our measures of central tendency. We have the mean, which is like the average value for all of our data points. And so kind of in general, how far away from the mean are most of the data points? Are they very clustered around the mean so that they're all very, very close to that mean? Say the mean height of our class is 5'6". Are most of us between 5'5" and 5'7"? Or are most of us between 5 foot and 7 feet, right? That would be a more dispersed data set, where the first would be a more clustered data set. So what you will see most typically is the range, which is going to be the minimum value and the maximum value of the data set, and then also the variance and the standard deviation. So the standard deviation is a bit easier to interpret because it's in the same units that our data is in. And so you can think of it as being the typical distance from the mean for the data points. And so again, these functions are very simple. We have range, variance, and standard deviation. All right, so let's see what is the range of our fertilizer experiment growth. So it ranges from 1 to 2 with a standard deviation of 0.45. Summary is also very handy. It gives you here the minimum, the maximum, the median, the mean, and also the first and third quartiles. And so this gives you a good idea of the distribution of your data. But what gives you a better idea of the distribution of your data is something that's visual. So we're going to start with data visualizations now, which is something we'll be doing for the rest of the semester and something that I feel passionately about. So this is just an introduction to histograms. We are going to get more involved in making these plots in later lessons, and we're going to make prettier ones too. But this is a good way to be introduced. So first what we're going to do is create a little toy data set so that we can really see what histograms have to offer. So what I have you do is create a data set, a normally distributed data set, by using this function rnorm. And so what that does is it takes random draws from a theoretical normal distribution that's defined by these characteristics, right? So we are going to take 100 draws from a normal distribution whose mean is 75 and whose standard deviation is 10. I have you set a seed right here, which really just means R uses a pseudo random number generator when it does things like this. And so for all purposes, kind of all research purposes, everything that we're going to do, these numbers can be considered random. What makes it pseudo random is that it's a computer algorithm, right? So somebody had to make it. And it starts at a certain point to generate these random numbers. So when you set a seed and include that as part of your script, if somebody else sets the same seed and then uses the same function to produce random draws, they will get the exact same numbers that you did. And in this way, we can make our research reproducible. So even in the context of this course, if I didn't set a seed and I had you guys create this data set with these random draws, even with everybody typing in the same function, we would all get slightly different numbers. And that doesn't do us a lot of good when we're trying to all be on the same page, right? So we are going to set the seed first, and that way we will all get the same numbers. And so let's create a histogram so we can see the distribution. Well, first let's look at this. So we could use that summary again to get an idea of our distribution. But I don't know about you guys, that doesn't really do me a lot of good. I'm not the sort of person that can look at that and really feel like they understand something about the data. Histograms are a different story though. So hist is the very easy, simple, built-in way to plot a histogram in R. So this is our data set that we created here, dat, which is a variable name that I use a lot. So let's run that and see what it looks like. And there we go. There's our histogram. So you can see that all of those values, all of those 100 values that are in our dat variable have been put into what are called bins, which are intervals, right? And so the height of each of these intervals corresponds to the number of observations that fall in that bin. And so you can get a sense of the distribution of our data set here. So normal-ish, we could say. But so very handy, right? But there can be issues with histograms too, especially making them an R and just accepting the default values. So let's create another data set to illustrate that point. So what we're going to do is take two draws from normal distributions that have the same standard deviation, so the same degree of variability, but with different means. So one is just shifted, they're shifted from the other. And then we are going to combine them into one sample. So we have our two draws here, and then we combine them into one sample. And so if we just run a histogram, accepting the default values, this is what it looks like, which, you know, we would be tempted to say looks like a very normal distribution, except we know from having created, having the luxury of having created the data set ourselves, that it's actually a bimodal distribution, right? Because it's actually drawing from two different populations with different means, and they're combined. But we can't see that here because of the way these bins have been constructed. So let's try it again. So see here, there are 6 bins. Let's increase the number of bins and see what it looks like. So you can see here very clearly that this is a bimodal distribution. And so that's just something that you have to be wary of when you're using histograms to explore your data. You want to look at a bunch of different bin sizes, and you also want to have an idea of what your data looks like and what it represents, so that you can make sure and capture all of the patterns that are there that exist in your data. So there are different things that are very easy to do to customize these histograms. You can add limits. Your axes, you can change them very easily. So you can make this y-axis taller because you see it doesn't exactly come up to the highest value. And so this kind of guides you through all this. You can also give it a title. You can change the color. It's all very simple. There we go. That looks a lot better, right? And so one thing I will say, just in terms of writing code for readability, you can see here that I've broken each one of these components of the function to a different line. I think this is way more readable than something like this. Which you'll see a lot in people's functions. To me, that's really hard to read and very confusing. So I think when you write it like this, it makes it a lot easier for you as well as other people to see and understand what you're doing. And also when you go back to something and you decide it needs to look different, you decide your code is not written quite right, it's a lot easier to change it. All right, and so one last thing that I have you do is plot on top of that histogram a curve showing what a true normal distribution, theoretical normal distribution would look like with the same mean and standard deviation as our sample so that you can compare it. And then you can tell me whether or not you think that this theoretical normal distribution is a good representation of our data or not, and why. So hopefully this tutorial did you some good. Hopefully I didn't go over things too fast. If you have suggestions or issues, please let me know. I'm definitely willing to tailor these videos to y'all's needs. So like I said, after you have run all of the code that is in this document and answered all of the questions in blue, you are going to create a section for your exercises. Oops. And then you are going to answer all of these questions. So I think before I had you actually writing the question in there. I don't need that, but definitely put the number on there, and you need to do it as a comment as well. So number 1, and then you write your code, and then you tell me the answer. And then same for number 2. Write your code and tell me the answer. And then you will save and you will turn in this script with, again, all of the code that you've run from the lesson, as well as the answers to the questions that are in the blue boxes and the exercises. You will upload that to the assignment folder on Blackboard. All right, happy Labor Day, y'all. Have a good one.